Right. So good. Continue. No. Oh, there it is. Right. Yes. So thank you for joining. Also, maybe I should say a couple of things. One is I don't expect to finish today. So if it's okay with the organizers, I will also use next time. And also I think today will be rather technical. So we will try to do something more slow and precise, and it would be more bread and butter than champagne. So if you have some expectation, it's more like a lecture, but in the sense that I'm not really an expert on this. I haven't taught this before, so that's probably also some misunderstanding from my side. So you're more than welcome to interrupt with questions and so on and ask. And of course, if the level is too high, you should say so and keep asking questions. And also, I should also say that all of the TOT seminars, they probably will be different in scope and so on. So if this topic about Spinors doesn't interest you at all, I'm very glad that you logged in, but don't feel obliged to sit, obligated to sit through a topic that don't interest you at all. I would like that we have an atmosphere where people just can come and go, and you don't feel that since they logged in, then they have to watch something. But that's one side of the coin. The other side of the coin is that you are more than welcome to try to get to something that you think is interesting by participation and try to ask questions and so on. So today, I guess what we originally wanted to do was to talk about Spinors in various dimensions and signatures, but I realized that before we can talk about that, it would be good to discuss the Clifford algebra. So basically today will be, I think, mostly about the Clifford algebra. And then next time we will get into spinor representations and so on. But for now, we will just work at the classification of Clifford algebras. And so, of course, the first point is, of course, what is a Clifford algebra? And so let me put in some notation. So, I'm thinking, of course, from string theory, where we have 10 space-time dimensions, or in theory, so there's a lot of space-time dimensions. And then, of course, we want to think of that as 4 dimensions plus 6 compact or whatever. So therefore, I chose some very big Lorentz index, because I was thinking that the 10D should probably be something smaller. So M and N is supposed to be mu and mu, our Lorentz indices. And we have some metric, and it would be diagonal of 1, 1, and then -1, -1 a couple of times, and then we would have S for space and T for time. So we imagine that we have some signature S, T for the metric, and then of course S plus T is equal to the dimension D that we work in. And then the Clifford relations are some gamma matrices, M, comma, Mn, and we have some anti-commutator equal to 2 eta Mn times a unit matrix, where so M and N runs over space-time indices. And already at this point, I should warn you about conventions, because of course there is one convention with the choice of metric, whether you East Coast or West Coast and so on. And the other choice is the sign in front of the Clifford algebra here. So there's actually 2 possibilities here. So that actually makes 4 possibilities, 2 for the metric and 2 for the choice in front of the Clifford algebra. So I will fix this to be plus here always, but that has consequences. So that means that you might think that what I call T for you would be space dimensions, and what I call S is time dimension for you if you have another choice of metric. Does that make sense? People are very quiet. So I just, so this is just my convention. I put a plus here. And then of course I would have to deal with it, and S and T might be precisely the opposite of what I write here. Does that make sense?
Yeah, I think it's fine.
Yes. Okay, so that's the first thing. And then the next thing is that normally we would think that these gamma elements are matrices, and we would say that they are n by n matrices, and where n is the integer part of d half. Okay, and this maybe is a place to stop. Where did I get? Oh, sorry, it's not n by n. It's 2 to the n times 2 to the n matrices. Dimension, and then maybe it would be good to understand where this 2 to the n comes from. Why is these Clifford algebras have this dimension? So this I thought would be quite useful for you to understand. And of course, this historically with Dirac, of course, this was back to where Dirac he was trying to find the square root from invent his Dirac equation from square root of the Klein-Gordon equation, and then he realized he had to use 4x4 matrices, and 4 is of course 2 to the n, and in 2 space-time dimension n is in 4 space-time dimension n is 2, so he had to use 4x4 matrices, and so the point is basically when he tried to find the square root of the Klein-Gordon equation, he ended up with having to satisfy such a Clifford relation, and then what dimension should we choose? So I thought that it would maybe be nice to give a proof in general why the dimension is what it is. So the point is that when we look at if we have the Clifford algebra, which I think I will discuss a little bit more carefully what it is in a minute, but I think for now, let's just call it C. And think of that. So imagine if we have, so the point is, what I want to say is that if we have a vector space here, which is supposed to be a representation of the Clifford algebra algebra C, and then so I want to think of it as endomorphisms of this vector space V. So this is some finite dimensional vector space, and it should be we would like to give a representation of the Clifford algebra on this vector space. And the first thing is that we will now define some. So the first thing I will do is that this vector space could, in principle, be an F vector space, where F is a field that's either the real or the complex. And the point is now that we can always think, we can always complexify and think of a complexified vector space. So and when we do that, then it turns out that a complexified Clifford algebra. So that means that we can multiply some of the elements with I here, and then we can get rid of the signature. So I will now talk about the representation theory for a complex Clifford algebra. For a complex Clifford algebra, the signature doesn't matter, because we can they're complex. We can always multiply with complex numbers, so we can put an I here and I here, and then we can get rid of a minus sign. So we can always assume that we have gamma m gamma n is equal to 2 delta m n unit, like this, for simplicity. So that's the first thing. The other thing is that we can now, so by complexification. So now the next thing is that let's define the antisymmetric combination of two elements. Like this. And then we will now look at n.
Klaus?
Yeah.
I think the last thing should be with minus.
Well, oh, thank you very much. Minus. Right. So now we want to pick we want to pick the following elements. So let's define H R to be I gamma R. So I guess I should use capital R comma N. Oh, and that's little n here. Gamma like this. So and I put an I here for convenience. I define H to be this, and then so I will have a list of elements that will be Hamiltonian, so to speak, that I will be particularly interested in. Here R runs clearly runs from 1 and up to n. So I pick these, and so I have H1 up to Hn, and now we can be in this unlucky situation, or it's not really unlucky. Well, half of the time it happens that the dimension is odd, and in the odd dimension, then when we have then basically we would have one more, so plus gamma d, also it's gamma d if d is odd. So I have to add one more generator in the odd case. So I have n always, and then plus one more if d is odd. So I will look at these elements, and the point is that these elements they commute, they are mutually commuting. So I can take H R and HS and see that that's actually 0. Also it's easy to see. Yeah. So one thing that you can see when you have a Clifford algebra is that when M and N are different, then the gamma matrices they anti-commute. So here we so therefore the gamma D will clearly anti-commute with all the gamma matrices which are inside the H, and H is 2, so therefore the gamma D will commute with the H's. So this gamma D clearly commute with all of them. What about the two H's? So the point is now that if we take 2, yeah.
What is the n for each R? So you fix R, and what is that n you're adding to the second slot? I don't understand.
N is so n for the next 2 lectures would be this number. It would be a d half integer value.
So it's for all the R's, like those HRs, those Hamiltonians as you call them, the parton of
so R runs from 1 to n.
Right. Okay. And it's just and it's just the half one. I see. And then I see.
Yeah. So there's roughly speaking half there, the first half. This is the second half, and then even in D dimension there's one more element. So I'm choosing this, and then I'm looking at the commutator of 2 of these H's. S for so this is only up to S and N only runs up to R and S only run up to N. I mean roughly half dimension. And the point is now that if the 2 R and S are different between 1 and N, then clearly the gamma matrices which are inside H, they would not talk to each other, so they would anti-commute. But there's 2 gamma matrices inside H, therefore they will commute. Does that make sense? I mean, there's 2 gamma matrices here, there's 2 gamma matrices here, and everything inside anti-commute with each other. So therefore, when you commute 2 of them, then you see that they actually or super commute through, then you will see that they actually are commuting. Does that make sense? I see Andre is nodding. The other thing that is nice is that if you take HR squared, then you get the identity. And that is, and this is why I put an I here, because when I have gamma, then so here I have, yeah, so the point is that I have an anticommutator here. But in the case where the two entries are different, then I know they anticommute. Therefore, instead of the anticommutator, I can either write one combination or the other with a minus. And therefore, I see that that when I take HR squared, then I have basically gamma r plus n gamma r, and then I want to have gamma r next to gamma r because gamma r is 1. So therefore, I basically get 1 twice, but I have to put a minus, and the two i's takes care of that. So I get a plus 1. Does that make sense? So, so I have, the point is that I have constructed n Hamiltonians, so to speak, plus gamma 1, which are commuting, and actually they are involution. The involutive, when I do it twice, I get 1. So that's another way of saying that they only have an eigenvalues plus minus 1. Okay, so so now if we have yeah, so now comes the most difficult step, which I will refer to as something which is called Lie theorem. And that states that it's possible when you have n intercommuting objects, then or n plus 1, then you can find a common eigenvector. So there exists a common eigenvector for h1 up to hn and gamma d. Gamma d in odd dimensions. So and for the case of all the Hamiltonians, the h's, I know that they can only have eigenvalue plus or minus 1. So I can write this as hr, or okay, maybe let's say h1. So let me call the eigenvector for v. So h1 of v is a plus minus j1 v, and the last one would be hn. V is minus 1 jn v. So that where j is the j's are numbers which are either 0 or 1. j1, jp, jn it belongs to either 0 and 1. So this is like a parity. So either the vector have sign plus 1 or minus 1, and that's given by this parity j1 up to jn. Does that make sense? And the next we're going to do is we're going to apply the n first gamma matrices on this common vector. So we're now going to apply in various orders gamma and either 1 or 0 times. So let's make a new vector which we're going to call k1 up to kn index, which is equal to gamma 1 to the k1 up to gamma kn n to on v. And then again the k's goes from kn and they're either 0 or 1. So either we apply gamma matrix, then K1 is 1, or we don't apply gamma 1, then K1 is 0. So we can construct new vectors with indices, with some binary indices between 0 and 1 n times. Does that make sense? And by the way, just to this is of course the reason these vectors here we will later show that they are linearly independent, and these vectors are precisely 2n vectors, and this exactly explains why we have to have dimension 2n of a representation of the Clifford algebra, or multiplier of that. So the point is now that this vector.
Klaus, can I ask one thing?
Yeah.
So how many of the gamma matrices do we have now? Is there n or 2n of them?
We have in total, we are in d dimensions, so we have d gamma matrices. Of these d gamma matrices, we take half of them roughly, they end first, for instance here. But there will be a second half which we don't act, and then there is in odd dimension there will be one extra. So it's a little less or half of the gamma matrix we have here from 1 to n.
Okay, yeah, that makes sense. Thanks.
So now that so it's also a simple exercise to prove that HR with gamma S commute if R is not S mod N. So if and this is again because HR is has gamma matrix HR and gamma R and gamma R plus N, and if R and S is not like this, then the constituents they intercommute, and there's 2 here, so it's commute. And the other thing we can see is that HR with gamma R, they intercommute. That's equal to 0. And how do we see that? I guess it's easy just to write out what it says. I mean, it would be something like this is equal to 0. That would be that this is equal to I gamma R plus N gamma R minus plus gamma R plus N. Yeah, and this is 1, but the point is that 2 of these guys they anticommute. Oh, it should probably be a gamma here, not an R. So, but they anticommute, so this is 0. Make sense? Okay, so we have that, and now we can try to find what happens when we apply our Hamiltonians on all of these new V's here. So we can try to calculate H. Let's take H R on VK1 up to Kn here, and calculate what happens when we apply H on that. And the point is now that when we have HR, the only thing that we have to worry about is, let me see, that H actually commute with all the other gammas. The only thing that it doesn't commute with is it's the same R. So only the gamma R, and that anticommute. So basically what's going to happen is that I named that this is equal to -1, and then we get KR. So we get an extra minus because of anti-commutation, and then we get plus JR, that should be a capital R, and then JR, and then we get V of K1 up to Kn. So basically, it turns out that all the vectors, the other vectors here we define, they are also eigenvalues, eigenvectors of the Hamiltonians, and they are given by this prescription. Does that make sense?
Can I ask one more question?
Yeah.
So I don't know if you will be still talking about it, but you said that we can see that the dimension of the representation is 2 to the n because there's 2 to the n of these.
Yeah. Yes, I will be talking about that.
Okay.
That's the whole point, that we get to that. So the point is now that these Hamiltonians have a unique fingerprint on each of these vectors here. And we can, so the point is that they're either eigenvalues plus or minus 1, but it's, we can uniquely we can see that when we I mean we can think of this as a kind of a DNA code that tells us what eigenvector are we talking about. So when we apply the n different Hamiltonians, then we can ask n tests, and we get these results. And this result here will be unique for each of these eigenvectors. Is this clear? And that's another way of saying that these eigenvectors cannot be linearly dependent. They must be linearly independent vectors. All of this. So we have found out that there is at least 2n dimension of these vectors. Does that make sense? Okay. So this is basically and they are linear independent. I already said that. And then the point is now that we can now look at W as the span, the complex span of these eigenvectors V K1 up to Kn, where the case runs through these binary numbers, 0 and 1, like this. So and that's a 2n dimensional space. And then, but we only applied the first half of the gamma matrices on that. So now we can ask what happened to the second half and so on these gamma matrices. But that's quite clear, because now we're going to use the gamma of the last half. So that would be n plus r. So that's the second half of that's given by the definition of H as IH R gamma R. So the point is now that well, I mean, first of all, when we apply one of the first half gammas on these vectors, then clearly if there's already a gamma of that type, then 2 of them become 1, so we go away. So we cannot. When we apply the gammas, we will still be inside these vectors we have found, and when we apply the gammas here, we would still get gammas. They will still be inside the vectors, and H's, they're constructed so they're eigenvectors. So this would also be inside. So when we apply these guys, then we would still be inside W. So it's a stable. And gamma d in odd dimension would also, because it's already an eigenvector. So we see that W is a stable or invariant subspace. And I guess it's also pretty clear that it is that it's irreducible. So this basically shows you that whenever you have some representation of Clifford algebra, you will always end up with representations which are multiply of 2 to the n in dimension. Does that make sense? So the crucial thing here was the theorem here, which says that when you have commuting Hamiltonians, then they have a common eigenvector. Okay, so then of course we expect that the full representation theory I will assume that any representation of a Clifford algebra is completely reducible into irreducible representations of this form. Okay, so this explains why we now think of the gamma matrices as 2n times 2n matrices. Okay, so that was the first thing. So the other thing I should say is, so maybe at this point I should say a little bit more abstractly what the Clifford algebra is. And so the Clifford algebra, with space-time dimension S. So now I guess it's a little bit confusing, but there's only so many letters. So now from now on, and the rest, V will be the real span of the gamma matrices. So this now it's not a representation anymore. New notation. V is the span of the gamma matrices. So there's a vector space. And the Clifford algebra, the real Clifford algebra, S comma T over the reals, is then defined as the tensor product, the tensor algebra over the ideal, where the ideal is spanned or generated by the Clifford relations. So ideal I is a two-sided ideal generated by Clifford relations. So there is some subtleties here. So what do I mean by the tensor algebra? The tensor algebra, I mean, so I guess that would be the zero vector space. No, sorry, the field. The field, which is R plus, and then it would be, yeah, okay, so maybe I should say the tensor algebra is, of course, the direct sum over m equal 1, 0 to infinite of TMV, and the TMV means V tensor m times. So I should really write it, I guess it's R tensor R m times, like this. So this is called the tensor algebra. Okay, so now because I need sort of different tensor products, I will call this tensor product for dot. But it is still a tensor product. I will call it dot, but so I will call that the Clifford product. So here, I guess there's things to watch out for here. That I guess in the abstract setting, here I mean a dot between these here. So there will be a Clifford dot between two gamma matrices, and that's elements in this vector space here. And the identity, that's of course T0 of V is the field R here. So the point is now that I mean what you really have to be careful about is that there will be at least 3 different products we're talking about.
Can I ask Klaus?
Yeah.
Why do you call it a tensor product?
Because it is a tensor product. Yeah, okay. I think that might actually be clearer in a moment. So the point is basically that the ideal. So does everybody know what an ideal is?
Yes.
There's some. So an ideal is that when you multiply with the algebra here, in this case, or I guess it's ring in general, then you anything with ideal from the TV, you can end up in the ideal. So you have something that the ideal is generated by this relation with the tensor product here. So the products we will have, so that will be normally we will not write a dot, and then I will think of a matrix product. So there will be a matrix product, and then there will be a Clifford product. So here I'm not writing anything, so maybe I put it like this. That's nothing. I will not write anything when I mean matrix multiplication. And then I have Clifford product, which is a tensor product. I will put a dot. And then later I will need the tensor product to something else also. But it is a tensor product in the sense that that here what's happening is that we are dividing by the ideal. So here in principle this TV that is infinite dimensional here, but we are modding out by the ideal, and the point is basically that the Clifford algebra cannot survive more than that. Every time you have basically all let me see symmetric combination you can reduce with the Clifford relations, which I have here. But the antisymmetric you cannot reduce with the Clifford relation. So the point is that if you have 2 gamma matrices starting from T2, then you can, if it's a symmetric combination, then you can reduce it with the Clifford relation into something that belongs to T0, and so on. So therefore, you actually end up, you cannot, you can only, the only thing that can survive is anti-symmetric combination, and this actually is truncated by the dimension. So, so you cannot get arbitrary high order in this tensor product or Clifford product. Does that make sense?
No. Oh, so first of all, are you in your Clifford relation? Are you not using matrix multiplication?
No.
So gamma matrices are not matrices, or what?
Abstractly not. Yeah, of course. In the yes, I'm using. If I have a representation of it, yes, I will use matrix multiplication. Yes, but as abstract elements, it will be the Clifford product that's is used. But we will see that many times we can replace the product with ordinary matrix multiplication.
Okay, so it's some kind of abstract versus representation.
Yes. Right. So that's one thing. Yes. So the other thing. So the other thing I want to say is that, of course, we want to talk about the Lorentz group. I call it Lorentz group, even though I'm in arbitrary signatures. Of course, you could just be the orthogonal group. But independent on the signature, I will always I will think of this the element connected to the identity.
I was just gonna say that this tensor product versus multiplication, it's like as if you had the similar situation as in universal enveloping algebras versus Lie algebras, right? Like when you have the product in Lie algebra and you have the product in the universal enveloping algebras, and they're linked via that ideal, and then when you're actually representing that universal enveloping algebra, you're getting rid of the product and you're applying consecutively those generators as they come in the abstract tensor string, right?
Yes, yes. Your sound, I don't get you, Andre. Your sound is not so clear for me. I don't know what everybody else said.
Well, I don't have anything.
Anyway, I understood what you were saying, and that's yeah. So yeah, as you said that exactly as Andre say that the definition of a Clifford algebra is very similar to the definition of a universal enveloping algebra for Lie algebras, where you have a similar construction where you mod out by the Lie algebra relation instead of the Clifford algebra relations. And then we have the adjoint representation we can act on. We have the vector or the adjoint representation of this group acting on V, which is basically our space-time here, V there. Which of course have an inner product structure from the etas. And then let's also for later introduce gamma M1 up to MR equal to the anti-commute M1 up to MR. So I'm just we did it for two, but we can of course have a construction here where we take anti. Oh, I guess we should have a gamma also here. So this is basically 0 if some of these are identical, and it just becomes gamma 1 up to gamma MR if they're all different. If they're all different, then it's this. Of course, to have that, then in this I have an implicit on 1 over R factorial inside the definition of the anti-symmetrization, and if some of them are the same, I get 0. And here I guess we would use matrix multiplication. So and then the Lie algebra generators for SOTR, they are of course given by sigma mn, and they are half these gamma mn. And you can check that they satisfy the Lie algebra relations. Gamma sigma mn with gamma L anticommutator is given by gamma m eta n L minus gamma n eta m L So you see that that the V algebra actually is act on our vector space of gamma matrices, and of course they also act on each other to form the well-known Lorentz algebra, or whatever signature we are talking about. So it will be something like sigma Jm times. So I'm looking. Sorry, this should be Jk, and then I would have Ml here, and then for some reason I have Lm. And here Jm, and then I have eta Kl plus 3 more terms that I hope everybody is familiar with. Then let me also mention, but this is mostly for later. I just want to also mention something called a pin and a spin group. So to define that, I would have to define the set of units. So let S of V it be equal to the gammas in our vector space of gamma matrices, such that eta gamma gamma is plus minus 1. So I chose the S for sphere, but obviously it's not a sphere if we are in indefinite metric. But it's basically where the metric is equal to 1 or minus 1 of elements of the vector space of gamma matrices. So you can think of that as sort of a sphere on this vector space. And but it's the space of units, and the pin group is defined as the pin of V is defined as the union of spheres under the Clifford product divided by the ideal, and the spin of the spin group of V is given by basically half of that, but we only take the even products, Clifford products. So it's basically that cup of K belonging to 2n S. Oh, here of course I mean S K times, and here again SV K times, and again divided by ideal. So I just throw this out for now, now I want to be much more concrete and give so this was some abstract nonsense, just to give you a flavor of where this might be heading with the spin. Maybe you have heard that spin are double covers of the Lorentz group, for instance. Okay, so the next thing is to have how do we make a basis in practice? Well, how do we make a basis from Pauli matrices? And the basis, so we will start in Euclidean signature. So I will put an E on my gamma matrices to to say that it is Euclidean, and I will use a double index for these matrices. So here gamma EJ2, where so J runs from 1 and up to n, so the half, so to speak. And this, what the construction we will do is what I would call the Jordan-Wigner-Mandelstam half string picture. And this is because the way to think about this is very similar to what you know from anions and how to construct. There's a half string. So this will be so then you will have a geometric picture how to think of these quite strange formulas. But let me start with the strange formulas. So so now I would introduce a tensor product. This is why I reserved the tensor product for now. And then I have the sigmas would of course be the Pauli matrices. And then I would be sigma 1. And then I would have the identity, 2 by 2 identity matrix. And then I would have tensor n minus j. And for the same sigma 3, tensor j minus 1, tensor sigma 2, tensor 1, tensor n minus j 2 times 2. So so here I'm using the tensor product of 2 by 2 matrices, and there's n of these. So so the gamma matrices here becomes 2n times 2n matrices. Does that make sense? And now we will have to check that they satisfy the Clifford relations. Oh, I should say in odd dimension, we throw in gamma star, which is like gamma 5, but now with arbitrary dimension, which is 3 tensor n. So I claim this we should use from the last one. So now let's check that that this actually satisfies the Clifford algebra, which I think I actually erased, but I hope everybody remembers the Clifford relation. So the point is basically that notice that it's mostly sigma 3 and unit matrices, but there's only one sigma 1 and sigma 2 in these. So we have half of the gamma matrices is with one sigma 1 and the other is with one sigma 2. And the point is now that when the sigma 3, they basically you can think of so the half string picture I'm talking about is that you have like a string going up to position the jth position where you have a sigma 1 sitting here, or you have a string up here to the jth position where you have a sigma 2 sitting, and then on one side you have just identity matrices, and on the other side you have just sigma 3s. And the point is now that if you take, for instance, the same here and ask what is when we multiply this twice, then obviously you would get the identity, because sigma 3 with the sigma 3 is 1, and sigma 1 with sigma 1 is 1, and so on. So you would just get the identity matrix. But more interestingly, and the same with this over here. But what happens if you have two different? Or we can also say maybe this is on the same position. What happens then? So if sigma 1 and sigma 2 are on the same position, then the sigma 1 and sigma 2 they would anti-commute, and then so these two would anti-commute, and if they are at a different position, what happens then? So that's where the string comes in. That when we commute, then the sigma 1 would anti-commute with the sigma 3 sitting here. If sigma 1 is a little bit more to the left when we try to commute that, and then they will anti-commute also. Does that make sense? I see Mikael is nodding. So, of course, I forgot to say how you multiply two tensor products of matrices. I mean, if you have a tensor product and you want to multiply another tensor product, then it's understood that you multiply each factor with itself. This is how the tensor product works when you multiply that. Is it clear? So I cannot see, not everybody has turned their cameras on, but I see many nodding that this actually gives you a representation of the Clifford relations. So that's how we would do it in Euclidean signature. And how would we do it in arbitrary signature? Well, that's quite easy. So we would say that gamma m should just be equal to gamma e m if gamma m is +1 and I gamma e m if gamma eta mm is -1. So then we can mimic negative dimensions, time-like dimensions by just putting in an I here. Then clearly you would get the right sign. So so now we have constructed a representation of the Clifford relations. And then let me also define the parity gamma r star. So by that I would just take m from 1 and up to 2n of gamma m. And so this is the parity operator or parity in and I want to do this in I will only take up to 2n. So if we are in odd dimension, I don't put in the last dimension. And let me put this arrow here to indicate that you are supposed to take the gamma matrices in increasing order. Of course, the order of the gamma matrices are important because of signs, but apart from that, so I just put that just to have a definite. So it written out, it just means gamma 1 up to gamma 2n. And I claim that this is equal to this is equal to I to t plus n sigma 3 tensor n. And the point is, I guess I tried to specify the order, but I guess the order is still not completely clear. So I guess here I want to take the 1 here, and then the 2 with j equal to 1, and then the 1 and the 2 with j equal to 2, and so on. So they will be nearest neighbors. So I have a sigma 1 and sigma 2, which is I sigma 3. So that gives me I to the n when I do this. No, then what do I get? I get I sigma 3, and then I'll get a sigma 3 here. And so the point is that the two next neighbors, if I had to write it out, would be something like that I would get the identity, because the sigma 3 would just produce identity tensor, and then I would get an I sigma 3, and then I would get identities again. So I would have that on the jth position. And then I have to product all of them, and therefore I basically get sigma 3 n times, and I get an I for each because of I sigma 3, and then I get another I for each time direction because of this configuration. So this would be the sign in front for that. So that's another way of saying that. So I will define the parity so when I square this here, sigma 3 squared, then I get -1 to t plus n sigma 3. Oh, well, actually that is identity. So it's their identity, and so to get rid of that, I will probably define it as minus I t plus n, and then what we had before, sigma r, like this. So I want to take away this factor here, so I can define sigma 3 tensor n here, like that. And then there is an interesting observation that if we are in odd dimensions, then we have to introduce the last gamma matrix we call gamma sigma. So we see that in odd dimensions, we see that that the product of all the matrices are proportional to the identity in odd dimensions. So how much time I have used now? I've used more than an hour. Okay, so yes. So at this point, I think maybe it would be good to maybe go to the classification of Clifford algebras. So where so now we can ask what happens when we take a tensor product of two Clifford algebras, to Clifford D, say the complex Clifford algebra, and we take another D prime complex Clifford algebra, and we tensor product them together, and we assume that this D is even dimensional. This is not to go up in dimension, this is rather to decompose the dimensions that we have. So we want to think of bigger Clifford algebras in terms of smaller. So can we make such a statement? And what would you expect this to be? If I write D plus D prime over C. Would you be terribly surprised? So the point is, if we can prove this, then we can basically, when we have a big Clifford algebra, then we can decompose it into smaller ones, and then eventually get so small that we actually can calculate it. So this will be the strategy. But first, we will have to prove such a thing, and we also would need to prove a similar thing for a real, and this is a little bit more complicated. And you might also wonder, why do we have to assume that D is even here? This will be clear in a moment. So we have here, and then tensor Clifford algebra of S prime, T prime over real, and I guess this is a complex, this is a real. And this is isomorphic, and there's actually two cases here. There's one which I think most would expect immediately, S plus S prime, and then it's T plus T prime. And again here I have to assume that this is even. So this, so I'm assuming that D equal to S plus T, of course, is even. This only holds if S minus T is 0 mod 4. It's clear that S minus T is 0 mod 2 because it has to be even, because S plus T is even. But only in half the cases we get this result. This is of course the real, supposed to be the real guy. And something funny happens when we go to the other case, if S minus T is 2 mod 4. It becomes equal to S plus T prime, T plus S prime over R. So the role at space and time switches for the two cases. And to see this, I will now construct a basis for the tensor product. So the basis I will use is gamma m tensor 1 and gamma r star. Hopefully I didn't erase that, it's up there. Tensor gamma m prime, where obviously n runs from 1 up to d, and m prime runs from 1 and up to d prime. So what you might have expected is that it should be gamma times 1 and 1 times gamma, but that does not work. And this is again because of this half string picture, that we have to introduce some object here which have some sigma 3s in it.
Can I add something?
Yeah.
You have the two different cases.
Yes.
S minus T is greater than 0. S minus T is smaller than 2.
S minus T is
equal.
mod 4.
Is it equal, not greater than? It's
Equal.
equal. Okay, I just didn't see exactly what you were.
Okay, so it means mod 4. So
No, it's the equal sign looks like a greater than sign to me.
This one?
Yeah. Okay. Yeah.
Better now?
Good. I'm happy.
Good. So I guess actually in mathematics, when it's mod something, I guess they always write 3 anyway. I hope, is it clear? So, so the point is that because S plus T is even, then I can subtract 2 T's and get S minus T. That also have to be even. But S minus T is then either 0 mod 4 or 2 mod 4. Because I already know it's even. And the funny thing is that I have to switch T prime and S prime in the second case. And let's see why this is so. So the point is basically that, so where do we have it here? I mean, first of all, we are going to use that gamma m and gamma star, they anti-commute. Why is that? Is that always the case? Now I'm worried about the last. Oh, D is even. Yeah. So first of all, the M, this is even. So we never had a gamma, the last guy in that case for the first copy here, the first factor. So gamma M will always anti-commute with gamma star, and I guess that's because that gamma star is a product 2n matrices, and it anti-commute 2n minus 1 time, and it becomes 1 with one of them. So you can convince yourself that they always anti-commute like that. And that's basically what we have to use. That let's see that so basically when so it's again this half string picture basically that that if you are inside this half here, then clearly this would just reproduce the Clifford algebra, and when you are inside this guy, then it depends on whether it would reproduce or not, is because gamma star I, when we square it, we might not get 1, we could also get -1, and that's given, as we calculated before, equal to -1 n, and I wrote n plus t up there, but I could as well write n minus t. That's of course the same mod 2 times the identity, and now I can rewrite this using that n is n, of course, in this case is the same as 2n is equal to d. So instead of n, I can write s plus t divided by 2. So this is the same as -1 s minus t over 2 1. So the point is now that if s minus t is mod 4, then I get a +1 here. Then gamma squares the +1. But if I'm in the opposite case where this is mod 2, then I get a -1 here. And this has the consequence that when for all these guys, then when I have multiplied with this guy, then they would effectively have the opposite sign if this is in the opposite case, and then all what I call space and what I call time will be switched. So this is why it becomes opposite for the second copy because of this. Does that make sense? Linus, you have a poker face. I cannot read what they. So okay, so that is the point, and this of course is much simpler in the complex case, but because in the complex case we don't care about the signature. So we get this. So I hope I more or less convinced you. Oh yes, then of course there is when there's one from this guy and one from that guy, and then the point is again that that then this guy would meet this guy, which is anti-commute with, and this guy would meet this, which is the commute with. So we would get something that anti-commute, and which precisely satisfy the Clifford algebra for the bigger space. Okay, so and then maybe for fun, let me write down the main classification, and then let's go in and see so let me start with the conclusion, and then let's work out some small example, maybe the last for today. So the point is that so I claim that the classification becomes CL for the complex case. It's the simplest, of course. So the classification is that you should take mat 2n tend to 2n C, so it becomes a matrix algebra of that dimension, tensor C of something I'll call H tilde if D is odd. And this H tilde, this is because actually it's because I in a moment will also define something I call C tilde, which will become which is R plus R. And this is of course the split complex numbers, or split or par complex numbers. So that's I call this C tilde because it's not quite C. The identity squares to 1. The imaginary unit squares to 1 rather than -1. So this I call C tilde. H tilde. It's defined as C plus C. So it's just 2 copies of the complex numbers. I call that H tilde. And I don't think it's not very nice. There's many things in quaternions that's called split quaternions and so on, but I think this is not what is called split quaternions. So I wouldn't dare to call it anything other than it's 2 copies of C. And it's very convenient to write it like that. Then for the real case, it's a little bit more messy to write down the full classification, but I will try to fit it into one formula in the same manner of that, with some compromises, of course. So I claim that CLS, T R is given by, so there will first be some real matrix. I will write a dot here for now, R, because I have to discuss the dimension of this tensor R. And then there will be C if S minus T is -1 mod 4. And it will be C tilde if S minus T is 1 mod 4. And then there will be a R, and then there will be a H factor if S, and this is crazy, S minus T is -2, -3, or -4 mod 8. So this is, and then by the dots here, I mean that you should fill in the dimension here such that the full dimension add up to the full dimension here. And then this, of course, what we see here is exactly because of quaternionic and representations, or Majorana representation and so on, that sometimes the size of this becomes bigger or smaller depending on exactly this feature. But this we will talk more about next time. But let's, for now, for fun, try to calculate the few, some small dimensions. So let's start with the complex.
Klaus, can I ask?
Sure.
What is in the last bracket? Is that h?
Yes.
Okay.
It should be. So it's x minus t is -2, -3, and -4 mod 8.
Yeah, it's just the field. It looks like M to me.
8?
No, the field, you have quaternions probably in the last one, right?
Oh, yeah, it's an H.
Yeah, it looked like M. Sorry. Thanks.
Okay, so yeah, and of course this is the famous mod 8 that you see. I mean, for instance, in K theory and so on, that you have here the classification mod 8. So let's take some simple examples. So let's take Clifford algebra 0, C first. So there we would just have the identity. So this would be pretty boring. So this is just the complex numbers. Then the next one, Clifford 1, C, that would be the identity, and then say 2 by 2 plus, and then we just have to take one gamma-like matrix, sigma 3, for instance, here, and this is precisely 2 copies of C. So I want to call this for this is C plus C. So this is what I would call H tilde. And then let's take the next one, 2C. Then it will be equal to C 1, 2 times 2 plus C, and then take sigma 1. And then I have C sigma 3. I take sigma 1 and sigma 3 because in the real case, it's important that they don't have, here I can take any 2 sigma matrices that would work. And then we should add the things that we cannot reduce.
Can I ask?
Yeah.
You say any 2 sigma matrix, but if you take sigma 1 and sigma 2, you get the same thing, right?
Yes, exactly.
It doesn't matter.
It doesn't matter, exactly.
Even if you have sigma 1 and sigma 3 there, you don't have the same thing, but sigma 1 and sigma 2, it's the same.
It's the same.
It doesn't matter.
Yeah, it doesn't matter, exactly. Yeah. It's just because I would, it will matter in the real case in a moment. But so now I will get sigma 1, and I guess at this point, abstractly here, I should have the sigma 3 dot, where we are actually not matrix multiplication, but we have the product of 2. So basically, because this is the 2-dimensional vector space we have here, so we are in 2 dimensions. So sigma 1 and sigma 3 is the 2-dimensional vector space that we have. This is the identity, and this is the second, what belongs to T2, and this is the highest we can have that could survive in this case. And the point is now that I can, in this case, I can actually get away with removing the dot because if I take if I think of it as products, then of course it would be I sigma 2. It actually mimics the same rules as if I use a dot. So you can convince yourself that that I actually can here in this construction I can actually it doesn't matter whether I think of this in terms of the abstract dot, or I remove the dot and think of it as matrix multiplication. And all of the relations, it's basically because the rules are already defined by the Clifford relation. So they give a mimic, of course, what you know from multiplying sigma matrices together. So you get that the same. And the nice thing about that is that if there is no dot here, then you see that this is exactly the span of all 2 by 2 complex matrices, and therefore this is the matrix, it's matrix 2 times 2 C. So I guess it becomes a little bit more delicate in the real case. So let's continue with the real case. CL 0, 0 R. Yeah, I mean, I could. The point is basically that we can also do the CL3 case, but then when we get higher than CL2, then we can use this reduction theorem to get down. So I will not do higher than 2, and let's do the CL0.0. That's just R1. So this is just R. Then the next one is CL 1,0. And in this case, it becomes R 1 2 by 2 plus R sigma 3. And here I of course choose something which is real matrices, and in this case it just becomes 2 copies of R, which are called C tilde. Then we have a C 0,1. In this case, we can think of this as R tensor R I. So I choose I because I need something that squares to -1, and I can use I here. So I see immediately that this is C. So I can think of the Clifford 0,1 as C. Then CL 2,0 R gets more interesting. So this is R 2 times 2 matrices plus R sigma 1 plus R sigma 3. This is supposed to be a 2. Plus, and then we get again this point with R sigma 1 dot sigma 3. And for the same reason as before, we can remove the dot. And this becomes equal to mat 2 times 2 over the reals. And then there is CL 1,1. In this case, we get R1 2 times 2 tensor R sigma 1. And in this case, I need a minus. So I'm going to use I sigma 2 plus R, and then I get higher one sigma 1 dot I sigma 2, and for the same reasons I can remove the dot, and I see that this is just 2 by 2 matrices, real matrices. So that is the same. So now the last case with less than 2 or equal to 2, that would be this case, and this is equal to R, and then I have to use 2 things that squares to -1, and I'm tempted to use quaternion, so I would write this as RI plus RJ plus RI, and then I again have the Clifford multiplication IJ. And again, for similar reasons, I can actually remove that and think of this as K, and therefore this one becomes equal to the quaternions. So right. So that's that is so this is interesting. Maybe do you want to see one with a little bit higher, how that will reduce, or is it clear? We could take, for instance, so let me take one which is a little bit interesting. For instance, CL2,1 over R. And in this case, I would write this as, the funny thing about this one is that this is precisely in the case where that I want to think of this as, I use CL1,1, and then maybe actually, well, actually, maybe this is more interesting. So 1,2. So then this would be CL2,0, and the funny thing now is, I think that CL2,0 0,1. So I'm a little bit confused why I write 0,1 here. Oh yeah. So this is an interesting case where we are in the crazy case here down here. So I'm taking CL 0,2, but 0,2 is mod 2, or mod 4 is 2. So therefore, I have to change the order of T prime and S prime. And this is why they normally you would think that it should be 1,0 that should add up to that, but I have to change the order here. Does that make sense? So now, and then we can use the results from before that we already classified this guy as H. That was what we did over there. And this guy we classified as C. So this is the combination H tensor C. For instance, oh, and by the way, we could also have done this in another way. So this would be equal to, we didn't have to choose this one. We could also have taken the CL1,1 tensor CL 0,1, I guess. This would also work. And now we are in the case 1,1. That's the normal case here, where S and T are the same, and therefore there's no mixing, and it's just adding up like this. And this we also found out what was equal to CL1,1 is equal to matrix 2 by 2, and CL 0,1 is C. So what we get here is from the other classification. They are of course the same. Is we get mat 2 times 2 R tensor R C, and that's another way of saying that this is actually the 2 by 2 complex matrices. So you can work yourself. You can work up higher and higher in this manner. And I claim that at the end of the day, you will get something like this as the structure. So I think I want to stop before 2 hours, and maybe very soon. So let me just say that that you can do a similar classification for the even part of the Clifford algebra. So the even part would be where you only take the even parts of it, where you have an even number of gamma matrices in the Clifford algebra, and you can do a similar classification for that. Did I write down that? So maybe I will just indicate and then stop. So I managed to put this one up here. So we have the even part, the Clifford of D plus 1 of C even part is isomorphic to the Clifford algebra in one lower dimension. And the Clifford algebra ST plus 1 over the reals in the even part is isomorphic to the Clifford algebra S, T over the reals, and the Clifford algebra S plus 1T, R even is given by, and then you have this again a funny change of signature in this case. So you can prove that these are isomorphic, and the proof is basically that so maybe I should write it like this. So gamma M, gamma D plus 1. So you take the last guy over here and identify with a gamma M prime. So you multiply them together, so you get an even element here, and you can convince yourself that that any even element can be written as product of these guys. So for instance, if I want to reproduce the even element gamma M gamma N, then I could write it as minus gamma M gamma D plus 1 and then gamma M gamma D plus 1. Well, I guess it also would depend on the signature of gamma D. But yeah, so that's basically the idea. Let me. I think I should stop here. So next time we will go in and discuss spinors and the various representations of spinors.
Okay, thank you very much for the lecture. So I guess I'll stop the recording now and give room to questions and discussions.
If there's questions, I don't know.
Yeah, so anyone, please feel free to ask questions or start some discussion.